Well, I was working up in Chattanooga. I had been there 4 years after getting out of Georgia Tech, and I heard about the space, not the space, but the missile programs going on down here. And I was curious. Came down for an interview just about the time that Explorer 1 was launched. Got hired a couple of months later. Went into the program coordination office and was there about a year, and then transferred to the ARPA, at the time it was called ARPA NASA Systems Project Office. Saturn was building up from starting with the booster in '58. From there on, it went to the Silverstein Committee report recommending using liquid hydrogen for upper stages, and we knew at that point we were headed to space. There was something new all the time. It was exciting. Big hardware was involved, ABMA beforehand, and then NASA after. It was just an exciting time for an engineer. I got involved with the Saturn program when I joined the Saturn Systems office, and stayed with it until I left in 1965 to go to MIT on a Sloan Fellowship. But during that time, we worked on procurement packages. I helped write the model specifications for the S4 stage and the S2 stage. That led to a bidders conference, and I was surprised at the end of the bidders conference. My boss, Oswald Longa, announced that I would be acting stage manager. Blew my mind. Well, it was the first hydrogen stage that NASA ventured into. We had a procurement process after writing the model spec. Douglas in Santa Monica won the contract. We had immediately after that, the announcement that Douglas got the award, we had a group of over 50 people from Marshall. Or actually, at the time, it was ABMA. It was in '59. We went out to see the contractor facilities and meet the people. But it was a real exciting trip out there, and we saw firsthand what was going on in the Air Force contractor side of the house. Here locally, we were involved with Chrysler and Jupiter Missile, Redstone Missile. So it was a new event for us. Hydrogen, liquid hydrogen, and then it gets gaseous in a hurry because it's at minus 423 degrees F. It's very volatile. The gas will go through anything, the finest crack. It was considered dangerous. But Convair out on the West Coast had been working with a Centaur stage using the RL-10 engine. And they were having some successes, but they had a lot of leaks. Well, somehow or other in our development of the S4 stage by Douglas, we didn't have a lot of leaks. It was pretty well contained. But it was still volatile, and you could start a fire in a hurry. S4 was the first hydrogen stage that we had, and the Saturn V came along between 1960 and 1962. The C5 configuration was developed. Well, during that period, it was decided that we're going to have a third stage like the S4, but it had to have one J2 engine, have a higher propellant loading, and have a lot of different functions. It was a natural choice for NASA to just say sole source the S4B because of the experience that Douglas had with the S4. I got involved with the S4 and the S2 with the Source Evaluation Board, which in itself was an exciting thing. It was manned by Werner von Braun, Eberhard Rees, Willie Motzik, headquarters procurement people, top level. So there I was, a naive kid, about 33 at the time, I think. And I was hearing these guys talk about the contractors, the capabilities, and how we were going to distinguish which one was the better contractor to select. And then recommendation was made to the NASA administrator, and choices were made at that level. Well, one of the criteria was that we make the interfaces between the stages simple. And the only interface is your structural tie-downs and electronic commands from a guidance system to the engines for gimbling, for separation. So the interfaces were relatively simple. And that was, I think, made integrating stages from different contractors a lot easier. The S2 started out with a procurement package in, I think it was 1960, no, 61, and the selection was made. But this was a year or 2 years, I guess 2 years before the final C5 Saturn V configuration was established. So North American was selected. I got to be acting program manager. Our project manager had to go ahead for a C3 configuration at that time, knowing that we were going to evolve into something bigger. But the government wanted to get the contractor on board so he could have the advantage of the preliminary design. In fact, he helped NASA with ideas on the Saturn V configuration. The Apollo program, oddly enough, was selected and given to North American Aviation, SNID, at Downey, about 2 months after the S2 was selected. And we were all really aghast at how can the government put two huge contracts into one contractor shop. But it happened. During the ensuing period, that period leading up to the fall of '62, both contractors did a lot of preliminary design leading up to the Saturn V configuration. This contractor, SNID and Downey, was harboring two major contractors within a half a mile radius. It was horrendous. I was out there for a year. After, well, it was in '62, fall of '62. I went out for a year, and I got a feel for the not the confusion, but the constraints that were involved in getting work done by the contractor, and it was pretty obvious that a lot of things were slipping. Well, both contracts proceeded. From that point, '62, when they were given a go-ahead, until '64. And progress was being made, but it was slow, and the schedule was obviously slipping. Costs were going up, and these were cost-plus fixed-fee contracts, so the contractor did what he had to do to meet the model spec requirements. It was a strange period, and during that period, S2 Seal Beach facility had been constructed, and they had started building the S2 bulkhead as well as the other components that make up the tank. When I left the program in '65. We had just completed a quasi-CDR. It wasn't the kind of CDRs we've had since then, but we accepted it because we wanted to get on with the program. And other than the problems with having so much work done in one shop and the delays, work was really accomplished. And by the way, when I first got out there in '62, the contractor was keenly aware of the problem, and he suggested that the S2 be transferred for development in Tulsa. They had a facility in Tulsa. So immediately, my boss, Oswald Longa, took umbrage with that. To have the S2 selected on the basis of development in Los Angeles, with the Seal Beach facility being built just strictly for the S2, it was unconscionable to move the S2 down there. Well, a compromise was made. We decided that I'll call it dumb structures that don't have a lot of complicated electronics, could be shipped down or sent down there for design and manufacture. These are the interstages, the thrust structure, but as far as the cryogenic tanks, they had to be kept, and the design and development had to be kept in Downey in Los Angeles, Seal Beach. Well, we could observe the fact that they were making progress in design. It was slow, and the crunch didn't come until the manufacturing of the Common Bulkhead started, and that was a difficult job. In late 1964, General Sam Phillips, who was headquarters head of the Apollo program, was aware of the schedule slips that were impending, the increased cost, and he initiated a bunch of Tiger teams. We came out to Downey, and we spent the better part of a month reviewing intimate details and organizations as well as design and development of the S2. And it was also being the Apollo spacecraft was also a part of that review. Small disciplinary teams would literally invade the contractor and evaluate the progress. That effort in '65 ended up with Major General Sam Phillips and George Mueller to write a letter to the head of North American. The result was the contractor assigned a new guy to head up the S2 program. They assigned a new guy to head up the Apollo program, and progress. Well, we had progress from then on, but it was still extremely difficult, really, for almost the rest of the program. He was like a fighter pilot, like John McCain. He knew his business. He early on during World War II, he and Bob Gilruth, who headed up the Apollo program at Langley, had solved a problem on the P-51. It was an air scoop problem, and that relationship, I guess, might have helped getting the Apollo program assigned to him. He was a unique guy, and we had several meetings with him, and he was solicitous, answered our questions, and sharp technically, and didn't let grass grow under his feet. Well, we were in that period in late '64 and '65 when Sam Phillips was doing his work with the review teams, and NASA had announced a possibility, an opportunity to get a nomination of people who would go to MIT on the Sloan program, and I volunteered. Well, I had to make the application. I went through interviews with the head of the program at MIT, and eventually I got selected. Well, that was at an inflection point of the program following Sam Phillips' initial operation out there, and I was given an opportunity to either stay on the S2 or go to MIT. Well, I wasn't going to miss that opportunity. While I was gone, I read in the newspaper events that occurred on the S2 program, one of which was the destruction of the structural test vehicle at Seal Beach. For me, being up in Massachusetts, it was a shock, but I could do nothing about it other than just absorb the fact that it happened. But I learned more about it when I got back a year later. The accident occurred. The tank broke. It had water in there to simulate the propellant loads, and of course there were actuators to apply loads to it. And the tank broke at 144% of ultimate load. The design requirement was 1.4, which the difference between that was negligible, and the test was evaluated as being acceptable, even in spite of the failure, and it demonstrated that the S2 tank was extremely efficient, but it was getting pretty close to the ultimate load factor. It was tremendous pressure and excitement to get things done. You could hardly talk too long to people about, like I wanted to know what happened, and everybody was too busy trying to get ahead of the schedule and get the project on track. It was a rather more than an exciting period. One of the other problems that S2 faced was the lunar lander program at Grumman was overweight, and there was nothing that could be done about it. So S2 selected to take weight out of the structure in order to increase or allow the added weight in the lunar module. Well, in doing so, they would go from one vehicle to another on redesign just to squeeze out weight. In fact, an extreme example, was one of the sections of the common bulk, the upper facing that faced the hydrogen tank, the hydrogen material. That thickness was about 25 thousandths on one section, plus or minus 5. Well, that material started out about 125 thousandths, the upper bulkhead on the common bulkhead, and they had to have lands about the thickness of that material, about 125 thousandths. So they went to chemical mill operation, where you take a caustic solution and leach out the material very carefully to get it down to the dimension that you want, like the 25 thousandths. That is an extreme of how they saved weight on the S2. It was a critical operation, and it was done very carefully from stage to stage. And as the program developed, S2 was able to eke out a little more weight each time, and fortunately, we had no problems with the common bulkhead other than learning how to make it, and that was a difficult job. The common bulkhead initially started on the S4 stage, and it was spherical, or hemispherical rather. It was just two clamshells with a phenolic honeycomb interface in between them, a sandwich, so to speak, bonded together. A rigid structure, very rigid structure. So the common bulkhead was initially started by Douglas. In the case of the S2, North American proposed a half ellipsoid shape, so that the height of the bulkhead was shorter, and of course the S2 is 33 feet in diameter, and that bulkhead had to be carefully designed for tolerances to mate up with the hydrogen tank above it and the oxygen tank below it. There was the interface between those two propellants. Of course, thermally, there's no problem. One was minus 423 and the other minus 296, about 26 degrees difference. But it was critical. If it broke, the whole thing would just be a ball of flame. In terms of time, it was all crunch time in 1965. We felt we had completed the design. The contractor had built a common bulkhead. He had built the stage at Seal Beach. The first one off the line was the S2 structural vehicle, S2S, and that failed. The next one off the line was the dynamic stage, and then the all systems vehicle. The all systems vehicle was a flight type first item off the line that was to be flight design. Because of all the problems that were viewed in the Apollo program, and particularly the S2, it was decided, a rather major decision, to have the MTF. In fact, it was started back in '63. NAA was directed in, I guess it was January of '65, that the all systems vehicle would not be tested in Santa Susana. It would be shipped down to MTF. All the subsequent flight articles would also go down there for being tested. This was a major change from what was originally planned, and it was quite an inflection in the program. But it was intended to save cost, have the testing done at a NASA facility. That was the first inflection in the program, that direction. And then at the same time, we had Sam Phillips' reviews. And all this time, hardware was being built. The S2S, the structural vehicle, was completed and tested and destroyed. The all systems test vehicle, the first flight type off the line to be tested, was in process and being built. In fact, it was delivered in the summer of '65 down to MTF. But by May of 1966, it blew up down at MTF. But it was not an accident involving cryogens. It happened at night. Somebody on the first shift had left some valves and switches in the wrong position, or in a position that, and the night crew had not been notified or didn't get the word, and they overpressurized the hydrogen tank with gaseous helium, and it blew. But the saving grace there was the time that it had spent down at MTF. They had run a number of short duration runs with the all systems vehicle, and about a week before it blew up at night, they had run a full duration test on the S2. There was some confidence there that it would work, but again, you lose a stage, you lose a lot of testing that you want to get information from. So the next item to be tested at MTF was the first flight article, S2-1. And fortunately, it went through the preliminary tests and a final full duration, and was shipped down to the Cape. The S4 and the S4B stages had internal insulation. Its construction, they made waffle cutouts on the inside of the tanks. It was an exact follow-up of what Douglas had done with the Thor vehicle, how they built the structure. So they had these pockets in the inside, about an inch deep, and they put insulation in there, and then they covered all these pockets up with a membrane and bonded it. And the idea was that liquid hydrogen on the inside of the tank would clearly penetrate that because hydrogen will go through almost anything, the smallest crack. And the theory was that in that space where they had this insulation, you'd have two-phase hydrogen. Close to the outer skin, it would definitely be gas. Close to the inside of the membrane that separated the space in between where they had the foam, it would be a two-phase with liquid on the inside and gas on the outside. It was a rather rudimentary method of insulating hydrogen, but that was the Douglas proposal. Well, S2 came along, and they decided they're going to have external insulation, and their plan was to make panels of similar material, of foam, and it would be bonded to the outside of the tank and then covered with a membrane. And the idea there, again, was inside the tank, you had liquid hydrogen at minus 423. The design for the S2 was to purge those panels which had honeycomb that was perforated so that the hydrogen gas could flow up through it. And the idea there was like similar to what Douglas had. On the inside, by the outside of the skin tank, it was minus 423. Outside these 1.5-inch panels, you'd have atmosphere air on the outside. And of course, it would be cold, but you wouldn't have minus 423 on the outside, but it would be cold enough that the atmosphere would frost up on the outside of the tank. Well, it was a more efficient thermal design, and the reason they did it was because the aluminum alloy that was used in the tanks, both in the S4B and in the S2, was 2014 T6 alloy, and at minus 423, it was a lot stronger. It reached its maximum strength, and the higher strength you can calculate, the less material you needed for the design of the skin, and it was a very efficient structurally, as long as the material was was hydrogen temperatures. But on the S4B, that skin was not that cold, so it was a less efficient structure. Insulation for the S2 evolved from these panels to foam. They found out that when these panels fell off, a quick way of fixing them was to use spray-on foam. And they were coming off every time you filled the tank and emptied the tank during prior launch, pre-launch operations. And it incidentally was later used on the E-tank, and in the later stages that were launched, they were wholly covered with foam. Well, my wife and I went down to the Cape for 7 months to get the Skylab ready for launch. And during that period, the next to the last flight, I think it was the 17th flight, it was a night flight. In fact, it was the only night flight. And while we were building up the Skylab and the VAB, it was being prepared, and we got our passes to go out to see it, and we got out on the highway adjacent to the VAB. My wife, my daughter, her husband, and we just enjoyed seeing all that fire. A night launch is something else. You have all this fire, the whole sky lights up. So it was an exciting time. But then after, I guess, 5-6 months later, we launched the Skylab and had some problems with that launch. Well, there were a number of concepts that were brought up. The first one, the initial idea, and it really started before I got there, was get man in space. How do we do it? The S4B is going to be in space because it's your third stage. let's make a hatch that can be opened. They actually designed a hatch at the top of the hydrogen tank with the idea that maybe a man in a spacesuit could get into the tank and do something. I mean, that was a rather primitive idea, but that was one of the first ideas and quickly discarded. But the hatch idea continued because that was necessary when we had the full-up Skylab. You had access to the S4B hydrogen tank, which became actually our space station, to go from the airlock module into the orbital workshop, it was called. Then there were other ideas. One of the prime ideas was the sun telescope. That became, and it was an in-house project. Marshall did. So there was a lot of effort inside the Senator toward developing that telescope. The interior of the workshop, from the time I got involved until then, a lot of ideas were developed, designs produced for the interior of the orbital workshop. We looked at what submarine life was for people in a confined area for a long period of time. We even visited one of the atomic subs out in San Diego just to see what the situation was to live in a confined area for, in that case, was 90 days. But our plans on the Skylab, the first mission was to be 28 days, the second 60 days, and the third 84 days. Three different separate missions. So it wasn't too unlike submarine life in a way. Well, one of the ideas, and a lot of people were contributing ideas, and they said, well, look, Raymond Loewy invented the Coke bottle shape. He's reputed to have invented the shape of the early Studebaker. That was the news, and he had a reputation for designing. He was a rather flamboyant individual, and so that NASA hired him to come down and look at what we were doing on Skylab, and he spent 3 or 4 days there. I even had a picture taken with him. His ideas were good, and we implemented most of them, such as the interior surfaces of the workshop were coated with plastic material over insulation, that was applied on the inside. He wanted it colored a pale yellow to make it a little more easy on the eyes. He gave us a lot of ideas for wardroom. The table in the middle of the wardroom had restraints where astronauts could straddle their restraints, eat their food, read books, whatever. Wardroom was a place to relax and eat. And we even had a window in there. He didn't make a lot of major changes, but he put on some polish. Well, the legacy of the Apollo program, to my mind, was that it was just another event in human history where individuals, human beings, decided to go beyond the next hill, go over the ocean, go to the moon. It was an event, I think, that was typical of the human beings, and it was, I think, the way we've been, as a species, we've been able to survive.